In the previous proposition, we showed that the definition of the affineness of a map between two normed linear spaces can be reduced to the case that f preserves any point on the line segment proportionally. Now, if we are given an additional hypothesis that f is also continuous, then this right-hand side can be further simplified to the case when f preserves just the middle point. So let me state this as our proposition 3. A continuous map f from E to F between normed spaces is affine if and only if for any A, B in E, f of A plus B divided by 2 is equal to f of A plus f of B divided by 2. And let's prove this. The forward direction is trivial because this is just a special case in the definition of affineness. The tricky part is the backward direction. We want to prove from the fact that f only preserves the middle point of any line segment to the case that it preserves any point on the line segment. And to this end, we'll need the following idea. The idea is that given any line segment from A to B and any point on it, we want to keep dividing this line segment into halves. And so that we can use this hypothesis on the right hand side. When we keep subdividing this line segment in halves, eventually we'll be able to approximate that given point on this line segment. So what we do is keep subdividing this line segment into halves to approximate any point on it. So that is the idea. And then we'll use the continuity of f to get the result we want. So that is the idea. But the idea is not a rigorous proof. To prove this rigorously, we need the mathematical induction. So we are going to prove the following claim by induction. For any A, B in E, and in the integer n greater or equal to 1, and the integer m between 0 and 2 raised to the power n, f preserves any dyadic subdivision of the line segment A and B. So we'll prove this by induction. And once this is proved, then since the following collection of points, namely all the dyadic numbers in the interval from 0 to 1, is dense in this closed interval from 0 to 1, all those dyadic subdivision points for all m and n satisfying this relation will be dense in the interval from A to B. And by the hypothesis that f is continuous, we have by approximation or by taking limits that f preserves any point on this line segment. And that finishes the proof of the backward direction. So all it remains to prove this claim by induction. I'll let you think about it for a while, and I will tell you the answer later anyway. To use the induction, I first need to specify on what integer we are going to apply the induction. We are going to apply induction on the integer n. When n is equal to 1, the left-hand side will be equal to the right-hand side trivially. By hypothesis that f preserves the middle point of any line segment. Because in that case, when n is equal to 1, m can only take values 0, 1, and 2. When m is equal to 1, that represents the middle point of the line segment from A to B. And when m is equal to 0 or 2, it will correspond to the endpoint, A or B. So this is trivial. Now suppose the claim is proved for all less than or equal to n-1 cases, and this is very important, all AB in E. Now, for any AB in E and integer n greater or equal to 1 and m greater or equal to 0 less than or equal to 2 raised to the power n, without loss of generality, we may assume that m is greater or equal to 0 less than or equal to 2 raised to the power n-1. Do you see why we can assume this without loss of generality? That is because if m is greater or equal to this guy, then we can swap A and B. So, otherwise, we may swap A and B. For the case when m is between 2 raised to the power n-1 and 2 raised to the power n. So, with this assumption, let's look at the dyadic subdivision point of the line segment from A to B. F of this point will be equal to, now we are trying to use this induction hypothesis. The trick is to produce a 2 raised to the power n-1 so that we can use this induction hypothesis. What we need to do first is that we're going to pull out a 2 from here, from the denominator. And we also need to produce a 2 raised to the power n-1 here. And we need to make this up by adding a b. So b plus this guy times b will be equal to 2 raised to the power n minus m divided by 2 raised to the power n minus 1 times b. Don't forget to divide this whole thing by 2. And now, we are going to apply the right-hand side of our proposition that f preserves the middle point of any line segment to this part. In particular, we're going to apply it when those 2 points place the row of the endpoints of line segments. So the right-hand side of the proposition gives us that 1/2 of f of this endpoint plus 1/2 of f of b. So this is by the right-hand side of our proposition. The next step is to use our induction hypothesis. We're going to apply this induction hypothesis to this part. And this gives us 1/2 times m divided by 2 raised to the power n minus 1 times f of a plus this coefficient times f of b plus 1/2 of fb. And simplifying this will give us the thing we want to prove. M divided by 2 raised to the power n times f of a. And if you add up this part and this part, you will get 2 raised to the power n minus m divided by 2 raised to the power n times f of b. That is what we want for this claim. So this finishes the proof of the claim by induction. And by our discussion above, this also is the end of the proof of the proposition 3, the backward direction.